Welcome. My name is Cory Cohen, and I'm the leader of the Executable Code Analysis team in the Threat Analysis Directorate at the CERT Coordination Center at the Software Engineering Institute. Today I'm going to be presenting with my colleague, Dr. Edward Schwartz, about advancing cyber operator tradecraft through automated static binary analysis. This presentation has been cleared for public release. On the Executable Code Analysis team, we've been building tools to solve DoD program analysis challenges for a while now. Historically, our work is focused on malware reverse engineering, but more recently we've also been focused on software assurance and vulnerability discovery. We maintain a platform that we call the Pharos Static Binary Analysis Platform. In this platform, we build a wide variety of tools that are focused on making a difference for operational DoD cyber tradecraft needs. The Pharos Static Binary Analysis Framework includes a whole bunch of features that are useful for building static binary analysis tools, and a number of them are listed in the blue box, and I'm not going to go into the details of those, but suffice it to say that they're useful for building tools like the ones we're talking about. The Pharos Static Binary Analysis Platform is built on top of ROSE, which is maintained by Lawrence Livermore National Labs, and we have a very close partnership with them. Their ROSE compiler framework is highly extensible, BSD licensed, and implemented as a C++ library. As a consequence, our Pharos framework has many of those same properties. Our Pharos framework is available on GitHub at the URL listed on the screen and on the board behind me. We've built a wide variety of tools in the Pharos framework. Today, the only one on this list that we're going to be talking about is OOAnalyzer. But I wanted to give you an idea of the other kinds of tools that we've built in the framework, so that if you visit our GitHub website, you can look for things that might be interesting or relevant to your operational needs. For today's agenda, we're going to discuss 3 examples of how the Executable Code Analysis team has been advancing cyber operator tradecraft through automated static binary analysis. The first topic is program reachability for vulnerability and malware analysis. This is an early research topic where we're trying to bring the very best academic research to bear on new problems in operational use. The second topic that we're going to talk about is recovering meaningful variable names in decompiled code. This is an instance where the team has built a prototype tool. We've been testing it, and it's basically ready for transition, but we haven't actually transitioned it quite yet. In the third section, we're going to be talking about object-oriented construct recovery using our tool OOAnalyzer. This tool has been fully transitioned. It's been in use by operational DoD operators for a while, but we've been making improvements and maintaining it to better meet the DoD's needs. In this portion of the presentation, we're going to be talking about an early research topic that the team has been investigating: program reachability for vulnerability and malware analysis. The problem that we're facing here is that highly skilled Department of Defense malware and vulnerability analysts currently spend significant amounts of time manually coercing specific portions of their executable code to run. Basically what we're saying here is that they have a vulnerability or a piece of malicious code that they'd like to see execute. They don't know how to get it to execute. And so they have to figure out how to execute it before they can begin analyzing it. Our solution to this problem is to automate the analysis of the binary code, choosing program inputs that trigger specific behavior, and then to reduce the time that the cyber personnel spend performing these complex software analysis tasks about under what conditions the code is reachable. Our approach is to use techniques from the software model chalking community to identify these inputs and to generate a simplified executable that's free of all these complex and convoluted dependencies, so that the analyst can put it in a runtime environment, and when they run it, it'll just execute right to the parts of the program that they're interested in observing. This diagram shows the architecture of our proposed pathfinding tool. On the left-hand side is an assembly language listing that has some code that's of interest to the analyst. It might be malware, or it might be a vulnerability that they're interested in demonstrating. And the analyst wants to know, under what conditions does this malicious code or this vulnerability execute? So our approach here is to take this assembly listing and lift it into an intermediate representation and then express that intermediate representation as what's known as a Z3 SMT constraint problem. SMT stands for Satisfiable Modulo Theory, and it's an area that's been getting a lot of research in program analysis over the last several years. Basically, it takes an algebra problem, a Boolean algebra problem, and says, is this satisfiable given all these constraints? Which we can think of as, is this code reachable under a given set of input constraints? And the SMT solver will come back and either say, no, this is not satisfiable, or yes, it is satisfiable, and it's satisfiable under the following conditions. For example, when the ECX register is 42 hex, and when the check system call returns 34 hex, then the point in the program that you were interested in reaching executes. We can use that information to perform the transformation of our executable code to produce something that will run directly to the interesting parts when executed. In this research, what the team has been doing is it's been evaluating multiple different approaches and implementations to generating that IR and proposing or constructing the SMT constraint problem. We've looked at 4 different approaches: the Pharos function summary approach, the weakest precondition approach, the property-directed reachability approach, and a Ghidra Seahom-based approach that also uses PDR. We've been evaluating each of these approaches for accuracy and scalability to try and understand which one best meets the needs of the cybersecurity operator analyst from the DoD. So the first approach that we've been looking at is the Pharos function summaries approach. This is the one that's been historically used by the Pharos static binary analysis platform in tools like OOAnalyzer, which we'll talk about a little later today. This approach is an approach that's designed to be simple. Memory is represented very simply and very efficiently as a scalar map that maps an address to a value. And while this is very easy to implement and works for some circumstances, it's not actually a very rigorous or robust way to represent memory. Loops are unrolled, and that means that there are some paths that we're not able to reason about correctly and that we're not able to prove are in fact reachable. Overall, this approach has proven to be great when it works, but we knew it had some limitations, and as we've been working through this research, we've gotten very effective at demonstrating exactly what those weaknesses are and how it doesn't really meet the needs of analysts in this particular problem domain. The second approach that we've been looking at is the weakest precondition approach, and this approach uses the Pharos static binary analysis framework to produce an intermediate representation. And this intermediate representation is much more accurate because it uses the full semantics of the instructions to model the program much more accurately than the Pharos function summary approach did. We've also represented memory more precisely using a single large array for the entire stack. And this has some performance problems. It's not the most efficient way to represent the memory, but it is much more accurate. And unfortunately, those performance problems could be an issue, but we've got some good news there, which is that the weakest precondition algorithm is known to generate formulas that are linear in size for the SMT solver. So there are some, it's kind of a medium balance here. Overall, we expect or know that this weakest precondition approach will be more accurate than the Pharos function summary approach, but the real research question going into this research was, can it be made, can the PDR approach do better? So this property-directed reachability approach, or PDR approach, it comes out of the software source code model checking community. And it's able to reason much better about loops, and we'll talk about that more in a moment. But the problem with the PDR approach is that it hasn't really been used on binary executables. It's a source code approach. And so to address these issues, we formed a collaboration with Dr. Ari Gerfinkel at the University of Waterloo. He's a world-renowned expert in Z3 and SMT and PDR, and in fact he's the creator and maintainer of the Spacer PDR engine, which is the PDR engine that ships with the Z3 SMT solver by default. And throughout this research, we've been working with Ari to improve the support for bit vectors and arrays and the portions of program reasoning that we knew were going to be problems in the binary domain in comparison to the source code domain. So this PDR approach, how does it deal with loops better? Well, it's able to reason about loops in such a way that it can make observations that the other two approaches cannot. So, for example, it's able to conclude that a particular loop will never terminate, and therefore the code after the loop will never execute. It's also able to reason iteratively and inductively over loops to figure out things like this loop may go around some some indeterminate number of times, but it always exits when x is equal to 3. Or it might be able to conclude that y is equal to 4, and because it's not modified in the body of the loop, y is also equal to 4 at the end of the loop. And these advancements in loop reasoning mean that we're able to reason about paths and their reachability much more accurately in the PDR approach than we are in these other approaches. We've used the same memory model and the same IR that we used in the weakest precondition approach, so we're very comparable there. But what's different about this PDR approach is that it's shown a lot of performance problems. It was designed for the source code domain, where the functions are all broken up into individual stack frames. And so this memory model, where we represented the entire stack as a single memory array, created a lot of problems, and it struggled quite a lot with performance. We've also noticed that the PDR engine occasionally gets stuck trying to guess the individual bits of a large register, like a 64-bit register. So overall, this approach is very accurate, but has some performance problems. This led to the proposal from Dr. Ari Gerfinkel that we try another approach, a Ghidra and a Seahom-based approach that also uses PDR. The observation that we made here was that the Seahom tool, which is the source code analysis version of the Spacer PDR engine, it was doing very well in the test cases that the PDR engine, our previous approach, was struggling with. So we had this idea that maybe if we could lift the problem to the same level of fidelity that the source code tool was already working on, that we would have a solution to our problems. So the idea was that we would use the Ghidra decompiler to produce something source code-like and lift that into LLVM and then invoke the Seahom source code analysis tool in order to get an answer for the reachability question. This approach has the same strengths as the previous PDR approach in terms of its loop reasoning, but instead of modeling the entire memory of the stack as a single big array, we're now breaking each function up into its own little memory array, which is accurate within the function, but saves the SMT solver from having to struggle through some of the interprocedural concerns. This approach is promising, but our big question here is how accurate is the decompilation, and how well can we really lift into LLVM and represent this source code version of the problem? So this slide summarizes our results, and I don't want you to dwell on the numbers. I just really want you to look at the colors. We've color-coded them such that red is the worst result for all of the approaches. Green is the best result for all of the approaches. And then there's two colors that are yellow, kind of a light yellow that represents the second place result, and a golden color that represents the third place result. We took 91 source code examples, and we compiled them at two different architectures, 32-bit and 64-bit x86, and on three different compilation levels, O0, O1, and O2, which we've labeled here as none, medium, and high optimizations. In total, this was like thousands of test cases. And I think the colors really help you see the trends here. They're largely what I've already talked about. The Pharos function summary had the most failures and the fewest passing tests, which means it really, frankly, did kind of badly. But it also came in first on the number of timeouts, having the fewest timeouts of any of the approaches. So this reinforces our idea that it's the least accurate and yet the highest performing approach. The weakest precondition approach is actually the one to beat. This is the one from the academic literature that we started with, and it's still doing the best. It had the greatest number of passing tests and came in second on both failures and timeouts, so it's doing okay there. But we know that this approach has known deficiencies, which is why we wanted to bring a more sophisticated approach like PDR to bear on the problem. So how did the PDR approach fare? Well, pretty much as we expected. It had the lowest number of failures, meaning that it was the most accurate, and when it produced an answer, it was the most correct. but the number of timeouts was the worst timeouts of all of the approaches that we looked at. And this was caused by those problems in memory modeling and bit vectors and so on. The Ghidra Seahom approach came out in kind of a disappointing third place. The good news here is that wasn't because of the path reachability problems that were causing the other approaches to have difficulty. The problems here were all in terms of our ability to accurately lift the binary into a source code representation and transform it into LLVM. So this means that longer term, if we can improve those pieces, this may turn out to be the best approach, actually. I think it's pretty clear here that there's no clear winner. They all have strengths and weaknesses. And despite, a couple of years of research here, we've not been able to make any one of these perform substantially better than the others. So in summary, path reachability and binary executables in particular continues to be a very hard problem. We've got all these approaches. There's the Pharos function summary approach, and it's not accurate enough. There's the weakest precondition approach that's technically the winner and does pretty well, but it has known deficiencies that prevent it from accomplishing our original goals. We've got this spacer approach, PDR approach, that is very accurate, but hasn't quite met our performance needs to be applicable. And we've got a Ghidra Seahom approach that's promising, but is stuck on other fundamental research challenges in raising the accuracy of the decompilation. The good news here is that we've got an excellent test suite. We're able to evaluate these very clearly now and very easily, and our team intends to continue to monitor each of these approaches in order to see which one eventually pulls out to become the clear winner in this race, so that we can solve this problem for the DoD at the appropriate time. We may also conduct some additional research into completely different approaches, like dynamic approaches involving concolic execution. At this point, I'm going to turn the presentation over to my colleague, Dr. Edward Schwartz, to talk about a piece of work on the team that's much closer to operational transition, some work we've been doing in variable name recovery during decompilation.
All right, thanks, Cory. So I'm now going to talk about a different project at the SEI that's a little bit farther along in the research pipeline, specifically how we're working to automatically recover meaningful variable names in decompiled code. So I want to start off by talking a little bit about the different types of tools that a reverse engineer has at their disposal. So what you can see here is an example of a very basic disassembler, which essentially takes the bytes in the executable and represents them in the form of assembly instructions. Now there are also more sophisticated disassemblers that make things quite a bit easier to analyze. They can be interactive, and they can have graphical interfaces that show you the control flow and the data flow in the program. And all of these things make it easier to analyze the program. But at the end of the day, the reverse engineer is still reading assembly code, which is not always easy, even for people that are very familiar with it. So a more recent trend has been the use of decompilers in reverse engineering. So a decompiler tries to reverse the compilation process. So as an input, it actually takes an executable, and as an output, it produces high-level source code, usually in a language such as C. So this is a screenshot of a very popular decompiler that's called Hexrays. And if we zoom in here, we can take a look at the type of output that it produces. And, it doesn't look like assembly code, and it certainly does look a lot more like C. But the longer that we look at this, we can kind of see that there's some aspects of it that are not normal for source code either. So it doesn't look quite like, normal source code we're used to reading. And there's a couple of reasons for this, but the one that I want to talk about today is that decompilers typically don't do much work to try to assign good names to variables. And let's look at an example here. So here's some decompiler output. And we can see that the variables are named v1, v2, and v3. So they're not really giving us any information about how those variables are being used. So the goal of our work is actually to take decompiler output like this and refactor it to add meaningful names to the variables. So for instance, we might call v1 fd, short for file descriptor. We might call v2 size, because it's used to indicate the size of a memory region. And we might call v3 ret, because it's used to temporarily store a return value. So that's the idea behind our work, is to actually give these variables names that will help the analyst understand what the variable is actually being used for. So I want to start off by talking about some good news, and that's we are able to actually recover up to 74% of the original variable names in a large corpus of code and executables that we gathered from GitHub. And we're really excited about that result. I want to talk a little bit about why that's actually possible for us to recover variable names in the first place, though. If you've ever worked in binary analysis, or if you just have a good understanding of how compilation works, you might have heard this common refrain that there's information, including variable names, that is simply lost during the compilation process. And there is truth to this. The variable names aren't stored by the compiler in the executable. So it's not something that we can simply, recover in a very easy fashion. So what we try to do instead is we actually try to predict a variable name in a statistical fashion by looking at lots of examples and looking at the context in which the variables are used. And some of the ideas for this type of learning come from a concept that's called natural language. So we know that natural languages like English can be really complex. So, we have poetry and we have really elegant prose. But the idea behind natural language is that actually most utterances, most of the things that we say or write, are very short and repetitive. And there's obviously some evolutionary reasons for this, right? If there's a predator or some other danger, we're not going to stop and write a poem about it. We're going to try to convey the sense of that danger in as few words and as quickly as is possible. Now, what does this have to do with decompilation? Well, a few years ago, researchers proposed a theory that software is actually natural as well. And in a similar vein, there are very elegant algorithms and implementations and designs, but there's also a lot of source code that is extremely repetitive. So the graph that you can see on your screen here is actually showing you the results from a study of repetition in a Java corpus of software. And the point that's highlighted on this graph is actually showing you that 70% of the sequences that are longer than 20 code tokens actually were written somewhere else inside of the corpus. And so the bottom line is that programmers are writing a lot of code that someone else has already written. And that's something that we can actually use to our advantage when we're trying to predict or learn variable names. So how does that work? What's the big idea? Well, we're going to learn what a typical or reasonable variable name is for a given context of code by looking at lots and lots of examples. And the idea for why this works is that if software is repetitive, then names must be repetitive as well. And I'm going to demonstrate this to you with a simple example. So here's a snippet of code, int main int, and then blank. And I want you to think to yourself, what code is likely to go under the blank? If I were to tell you that banana goes under the blank, I'm willing to bet that most of you will say, no, that doesn't seem quite right to me. But if on the other hand, I were to tell you that under the blank is argc, you'd say, oh yeah, I've seen that many, many times. That must be right. And so that's what we mean when we talk about trying to predict a variable name based on the context of the code in which that variable is used. So to learn how to name variables in this way, we need to have a lot of examples. And the good news is we can actually generate examples automatically. We need to start with code. So what we did is we scraped GitHub and we got lots and lots of source code. We then tried to compile as much of it automatically as we could, and then we took the resulting executables and we decompiled it using a decompiler. So at the end of the day, we wound up with this very large corpus where on one side of the corpus we have original source code with meaningful names that the programmer assigned. And on the other side of the corpus, we have the decompiler output with the placeholder names like v1, v2, and v3. So how many examples were we actually able to create in this way? Well, we created over 160,000 unique executables, which is a lot. And in those executables, when we decompiled them, we wound up with over 1 million decompiled functions. So quite a bit of examples. And then we split this information that we had by executable into testing, training, and validation sets, which we then used to try to automatically learn how to do this naming. So how do we actually learn how to name variables from all these examples? Well, we use them to train a neural network. I'm not going to go into a lot of detail here because, to be frank, my colleagues are really the experts on this. But at a high level, we use a technique called a sequence-to-sequence model, which consists of both an encoder and a decoder. Our model is a little bit unique in that it has two different encoders. We have a lexical encoder, which you can think of as essentially encoding the source code representation, and we also have an encoder that's structural, that takes information from the abstract syntax tree and encodes it into the neural network. And what we found is that we actually needed to have both of these encoders to be able to recover as many names as possible, which was a little bit surprising. We actually thought that the structural encoder would outperform the other one. So that's a little bit about how we actually do the learning, but what everyone wants to know is how well are we actually able to recover these names? And answering that question is actually a little bit difficult because what I think of as a good variable name and what you think of as a good variable name might not be the same thing. And so to avoid that whole subjectivity problem, we made an assumption that most of the time programmers give a variable a name, they think about it and they try to give it a good name. So we're just going to assume that names in the original source code are good. And that allows us to simply count how many times can we actually recover the original name from the decompiled code and use that as a metric to see how well we're actually recovering meaningful names. So I already spilled the beans on this a little bit. And remember that we're able to recover around 74% of variable names exactly. But one caveat is that we have a lot of data and we need to use all of that data to be able to get that level of accuracy. What this graph is showing you is that if you don't use all of the data or all the examples that we have, our accuracy drops quite a bit. The other takeaway when it comes to our evaluation has to do with code similarity, specifically how similar code is that we've trained on to the code that we're looking at. So in some cases in reverse engineering, you might be seeing new code that you've never seen before. But in a lot of cases, you've actually maybe seen that code before. This could be because of natural repetition, like we talked about. It could be because libraries get linked in to the executable, or it could be because code is copied from one project to another. So we observed this in our corpus because we saw functions, the same functions occurring in multiple executables. And so because of the way that we split our training and testing sets, sometimes that means that a function could occur in both the training set and the testing set. And that's something that obviously affects our overall accuracy. And that's what this graph is trying to show you. So if we have a function that is in both the training and testing sets, for instance, because it's a function that appears in a library, then we're able to actually recover names about 86% of the time. So we do a little bit better as you'd expect. If we look only at the results for functions that we didn't train on, then we drop down a little bit to 35%. This tells us two different things. One is that repetition and similarity are of course very beneficial and make it easier to learn how to predict a variable name. And two, there's a lot of repetition on GitHub, which we can see because our overall results are actually much closer to the 86% line than the 35% line. The other thing I want to mention is that not recovering the original variable name is not necessarily a bad thing, right? We can still recover variable names that are meaningful even if they're not the original. And I want to show you an example of that. So here's just another snippet of some decompiled source code. And the original names that the developer assigned to these different variables were file name, mode, and is private. So if we look at the names that our system was able to recover, we actually recovered file name and mode exactly correctly. But the third variable, we actually named create instead of is_private. So that might seem bad, but if you actually look at this code and see what it's doing, when that last flag is set, it actually creates a file with private permissions to make sure that different people can't read the file. And so, we're not naming the variable the exact same thing, but we're still giving it a name that reflects the way that it's used. And that makes it easier to understand and read the function, which is our ultimate goal. So one of the themes about our talk today has been about how we can take cutting-edge research and transition it to practice. And last year we actually talked about this project when it was really cutting-edge research. And And at the time, we had this proof of concept that really wasn't usable in practice, right? It was useful for us to demonstrate that this was theoretically possible, but a reverse engineer couldn't use it to actually look at code. So we've actually taken this and we've now implemented it as a hexphrase plugin for the hexphrase decompiler that makes it really, really easy to use this system to predict variable names. So here's a screenshot of hexphrase with the plugin being used, and it's a little bit hard to see, but all that the analyst has to do to actually trigger the system is press the P button on their keyboard to predict new variable names, and then everything else happens automatically behind the scenes. And I want to show you another example of what some typical results from the system can look like. We're clearly not getting the original variable names, but this is a good example of how we're still getting meaningful variable names. So we have names like the M for the environment, the return, the model, the width, and so on. These aren't exactly the original names, but they're still conveying information about how those variables are actually used in that code. And so they make it a lot easier to read. So in conclusion, software is highly structured and predictable. And we can actually use that to recover meaningful variable names by studying and learning on a lot of existing source code. We were able to recover up to 74% of variable names in our GitHub corpus, and the uniqueness and the similarity of the data is actually very important for predicting how well our system will work in practice. So with that, I'm going to turn things back over to Cory, who's going to talk about a different project, which has to do with recovering object-oriented information from executables.
Thank you, Ed. In this portion of the presentation, we're going to be talking about a tool that's actually reached operational relevance amongst reverse engineering analysts. Specifically, our tool called OOAnalyzer that's used for recovering object-oriented constructs from binary programs, and the improvements that we've been making recently to that tool in order to make it more relevant to the DoD. So what's the problem that we're tackling with this tool? Basically, that object-oriented programs are very complicated, and they have these abstractions that are time-consuming and expensive to reverse engineer. It requires very specialized skills that are in high demand in the DoD. Our approach to solving this problem is to combine a lightweight program analysis pass with our handwritten rules written in Prolog that express our knowledge as domain experts about how object-oriented compilers produce executables. In this way, we're able to fully recover the object-oriented constructs from an executable. So just to make sure that we're all on the same page here, when I talk about object-oriented abstractions, what are we talking about? Well, we're talking about the actual classes themselves, but we're also talking about the methods that are associated with those classes, the members that are associated with those classes and sizes and offsets, the relationships between the classes, such as inheritance relationships and composition relationships. Collectively, these are what I mean when I say object-oriented constructs. Our tool begins by recovering these from an input executable. We run our tool and it recovers these constructs, which are then provided to Ghidra and IDA Pro for interactive use by the analyst to understand what has been recovered. Our tool is composed of two components. One is a C++ component that extracts the facts from an executable using our Pharos static binary analysis framework. And the other is a Prolog component that has three phases. We engage in some forward reasoning, and then we make some educated guesses in a hypothetical reasoning step, and then we consistency check that representation of the program, and then we repeat this cycle. And I'll talk about each of those phases in some more detail. So a common question at this point is, why Prolog? Well, one of the problems that we face in this particular challenge is that there's multiple source code representations that can produce the same executable. This means that it's not possible to just reason forward and conclude what the right answers are about that program. We instead sometimes have to make educated guesses in that hypothetical reasoning component. And Prolog is very important to us because it allows us to backtrack when it turns out that one of those hypothetical reasoning guesses turned out to be incorrect, and we need to consider another alternative. We also really like Prolog because it allows us to express that expert domain knowledge that we've been talking about as rules in the Prolog language, which is a very natural and an expressive way to talk about that knowledge. So the first component in our tool is the Pharos fact exporter. As I've said before, it uses the Pharos framework, and it intentionally favors scalability and over accuracy. So we're using that lightweight memory model and path sensitivity that we talked about earlier in the pathfinding segment. We're not using any of the fancy constraint solving approaches, but this is sufficient because we've designed our Prolog component so that it's able to overcome any inaccuracies or weaknesses in this fact exporting phase. So what kinds of facts are we exporting from the Pharos fact exporter? Well, they're all very low-level facts. So for example, we're talking about how object pointers are passed between functions, and we're talking about which functions access which offsets in the objects, potentially representing member accesses. We're tracking things like which members were accessed before they were initialized, and what addresses might possibly be virtual function tables. At this stage of analysis, pretty much none of these facts have been proven to actually be object-oriented facts, and we'll do that in the Prolog section. So this is an example of some of those early facts that are reached through forward reasoning in the Prolog phase, built on top of those low-level facts. There are things like, yes, this function really is an object-oriented method, or this function is a constructor or a destructor, or maybe that there's class inheritance relationships or class composition relationships. These kinds of facts are the facts that reverse engineers are actually interested in order to understand the object-oriented structure of the program. So we've talked a lot about the expert domain rules that express what compilers do, but I wanted to try and provide a little more detail on that. In our paper, we've expressed these rules in the syntax you see here on the screen. And basically that says if precondition 1 and precondition 2 and precondition 3 and so on through some n preconditions, if they're all true, then that must mean that C is also true. And that would be an example of a forward reasoning rule. But we can also use this same syntax to talk about a hypothetical reasoning rule, where we interpret things very similarly, only now we say if all of these preconditions are true, that makes C a good educated guess. And we're going to try that first, and then we're going to run our consistency checking phase where we evaluate whether or not there's any contradictions in our model. And if there's not, we'll accept C, but if there is, we'll try not C instead and repeat the process and try consistency checking again. So here's an example of a forward reasoning rule. This one says that if a method is called on a base class object, then it cannot be defined on the derived class. This follows our normal thinking that base classes aren't allowed to call derived class methods. But you might be inclined to think that the right thing would be to say, well, then the method must be on the base class. Turns out that's not actually correct, because it might be on the base class or any of the base class's ancestors. Instead, you have to say simply that the method is not on the derived class, and then let a later rule sort out which base class it's on. So here's an example of a hypothetical reasoning rule that does exactly that. It says if a method is called on a derived class but not a base class, let's first assume that the method is on the derived class. If this guess fails, then it'll guess in a later rule that perhaps the class is in fact on the base class. So at this point, I'm going to turn things back over to my colleague, Edward Schwartz, to talk about how we've been improving the performance of OOAnalyzer to make it more relevant to DoD analysts. Thank you.
All right, thanks, Cory. So we published this work on OOAnalyzer originally back in 2018. And at the time, it really was an advance in the state of the art when it comes to research. As Cory described, a lot of this has to do with the unique Prolog-based design. But it's also unique in that it tried to recover information about all the classes and all the methods in the executable, which most existing work did not. And it was also much more accurate than existing work. So it really was an advance in the state of the art when it comes to research. But one of our concerns was that, because we wrote this in kind of a non-traditional language of Prolog, is it actually the state of the art in practice as well? Can it actually scale to the executables that we need it to be able to analyze? And to answer this question, we graphed some of the experiments we did in our original paper, and the x-axis here shows how many methods are in each program compared to the y-axis that shows you how long it took to actually do the analysis. And if we look at this, at first glance, it looks like we have a nice linear relationship indicating that it scales fairly well. But as soon as we start to zoom out and we look at some larger programs, we start to see that this relationship starts to degrade. Now, to give you some context, right around here, around 1,500 methods is an executable called MySQL.exe, which is the MySQL client of the database system. And if we zoom out a little bit more and look at some even larger programs, MySQL or the MySQL daemon for the server side of the MySQL system has around 50,000 methods. So it's quite a lot larger. And if you look at this graph and the trend line that we see, it's easy to see that MySQL D is going to take a really, really long time to run if it works at all. And that's very problematic because, DoD needs to be able to analyze these really large and complex pieces of software and to be able to do so in a meaningful amount of time so that we can take action on it. So what actually happens if we try to run OOAnalyzer on MySQL D? We ran it for about 18 days, and this graph is showing you the progress that it made over time, and the results were really disappointing. In the last 10 days, it made no progress at all. And this was really disappointing. Even though we were proud of the research that we did, OOAnalyzer was honestly too slow to be used on a lot of the programs where we really needed it the most, right? The most complex and the most large programs are where we need to have this automated analysis support. And OOAnalyzer just was not up to the challenge at that time. So this was obviously something that we wanted to make right. And so we set about trying to improve the performance inside of OOAnalyzer. Now, one of the things that you have to understand about OOAnalyzer's performance is that it very heavily relies on a feature that's called incremental tabling. And you can think of this essentially as memoization for Prolog. And the reason that's important is because OOAnalyzer is constantly trying to apply these reasoning rules, which you can think of as, if P, then Q. And essentially, if P hasn't changed at all, there's no reason to consider that reasoning rule because Q is going to be the same. It was either true or it wasn't. This has a huge effect on performance. And our original implementation of OOAnalyzer was built inside of XSP Prolog because it had a very mature implementation of incremental tabling, which we really rely on. So as you can imagine, we work quite closely with the developers of XSP Prolog, and one day they called us up and said, hey, we're working on trying to bring incremental tabling to a different Prolog system called SWE Prolog, and they wanted to use OOAnalyzer as a test case. And so that sounded great to us, being able to use OOAnalyzer on multiple Prolog systems, and so we agreed to help them out. It turned out this was a great decision and this benefited us in a couple different ways, but we didn't know that at the time. But one of the reasons is that SWE Prolog for our particular application turned out to be substantially faster than XSP just because of some of the design decisions and the properties of our particular application. But one of the other things that turned out to be very useful with SWE Prolog is it also has debugging and profiling tools that really allowed us to find the bottlenecks in OOAnalyzer and fix them so that we could start looking at larger and more complex software. So this is one of the tools that SWE Prolog provides, and it's called the resource timeline. And on the x-axis, it's basically showing you time progressing. And each one of these colored lines that you can see is showing you a different resource as it varies over time. So things like memory, the number of facts that we have at any point, the number of guesses, and things like that. The vertical black bars that you can see with the labels near them tell us which phase of OOAnalyzer is actually running at any given point. So this really gives us a good bird's eye view of how the analysis process is working and where we're spending the most time and resources. Now, on a more detailed level, SWE also provides access to a profiler. So like most profilers, it tells you, what functions are calling other functions, which you can see in a graph, how many times those functions are called, And probably the most important thing, if we zoom in here a bit, is it also tells us what percentage of our runtime is being spent evaluating different functions. And here, this is a big red flag. It's telling us that one particular rule, reason not merge classes Q, is using a third of all the runtime of the whole system. And so that's an indication that we need to look at that rule some more and figure out why it's using so much time. So what actually causes these performance problems? Most of them were caused by fairly simple mistakes. Just because of the nature of Prolog, one thing that can happen is that if you order your clauses in a poor way, it can have some fairly negative performance impacts. But the flip side of that is that once you've identified the problem, a lot of times you can fix those performance problems just by reordering things. And that honestly is the case for a lot of the problems that we found. Unfortunately, it wasn't the case for all of them. We also found a more systemic problem. So remember, I told you that because of incremental tabling, if no dependent facts changed, we didn't need to recompute a rule, and that saves us a lot of time. But what I didn't tell you was what happened if one of the dependent facts did change. And the problem is that we actually have to recompute the entire rule, including instantiations of that rule that have nothing to do with the fact that actually changed. And the reason this is actually problematic is because some rules are actually pretty expensive to recompute. And essentially, over time, as OOAnalyzer runs, we end up accumulating more and more facts, and so that means that the system ends up slowing down. And as we saw in MySQLD, this ultimately ended up to the point where we were essentially making no progress, even after running for days at a time. So our insight was that most of the rules at a logical level that we had are monotonic. And that essentially means that they don't need to be recomputed for new facts. The reason that they were being recomputed was because the Prolog implementation of tabling was just being a little bit conservative. So this actually inspired the development of a new type of tabling that's called monotonic tabling that's now part of SWE Prolog. And that has helped us speed up our code quite a bit. How much has it helped? Well, here's the before picture of our times, and the after picture is the red line at the bottom, and you can see that we're getting huge speed ups. In larger programs, we're getting 50 to 100 times speed ups. Remember I wanted to be able to run MySQLD in a reasonable amount of time, and now we're able to do that in enough time that we're still able to make an impact. If you remember this graph, right, we took 10 days of no progress when analyzing MySQLD. Now we're actually able to finish in about 33 hours. And just to give you an idea of how hot off the press these results are, since these slides have been made, we've actually brought that down to under 24 hours. So we're still making improvements and still making OOAnalyzer run faster than ever. So, in conclusion, Cory and I have just told you about 3 very different projects that we have going on here at the SEI that are in 3 very different stages of the research life cycle. We talked about some of our very early work on program reachability and how that early work informed us that there's not going to be a silver bullet solution, and we're going to have to continue that work in the form of a hybrid approach. We talked about our work on variable name recovery, which was initially a very early prototype that worked in theory but couldn't be easily used by analysts. We're now working on a plugin inside of the Hexrays decompiler that will allow analysts to literally receive better variable names at the click of a button. And finally, we talked about OOAnalyzer, which was a tool that we had actually previously transitioned, and we talked about how it still had some limitations that prevented it from being used on large and complex software. We made it significantly faster, and now it can be used on much larger and much complicated software. So these 3 projects show that research is extremely important, but it also takes a lot of work to really bring research to see the light of day and have it be used by customers in practice. And that's exactly what we do here at the SEI. We take great research, we work on great research, often in collaboration with our partners on campus, and then we transition it into a form such that it can be used in practice. So I'd like to thank you very much for your attention. Cory and I would be very happy to answer any questions that you might have about these 3 projects, or if you have any questions about binary code analysis in general at the SEI, we'd be happy to answer those too. Thank you very much.
Hello everyone, my name is Jeff Gennari. I'm one of Ed and Cory's colleagues here at the SEI. On behalf of us all at the SEI, I'd like to thank you for joining us for the research review. At this time, Ed and Cory are going to be available to answer some questions that you may have about their presentation. You can type into the YouTube chat. I'll act as the moderator, reading them aloud to you, reading them aloud to either Ed or Cory, who are responding in kind. So I want to start with some of the questions that, well, first, welcome Ed and Cory.
Thanks, Jeff.
Yep, good to see you guys. I want to start with one of the questions we received during the presentation. So Ed, this is from Greg, and it's about the variable naming or variable name recovery work. Is there a way to track the confidence of the neural network for a given variable name assignment?
Yes, that's a great question, Greg. So the way that the model that we trained actually works is that for each possible naming of a variable, the model is basically trained to give it a score. And then we basically pick the variable that has the highest score. So internally, when you ask the system to give you a set of new variable names, you do get these scores along with it. So right now, we don't present that to the user, but you could imagine trying to use these to kind of have some kind of filter, so that if we have a really good name that we have a lot of confidence in, we're going to go ahead and maybe automatically rename those variables to the ones suggested by the model. And maybe if there's a variable that we don't have quite as much confidence in, we'll present it as a suggestion to the user, and then they can decide to use that variable name or not. One of the other things that's kind of nice about that is that we don't have to pick a single variable name. We could actually give the analyst the set of the top 10 variable names that we have the highest confidence in. And a lot of times, that can give you a pretty good idea of what that code and what that variable is actually doing. One of the other things I wanted to mention is that it's actually a little bit hard to talk about what a good variable name is. So when we talk about confidence here, we basically mean our confidence that we've guessed the original variable name, but that's not necessarily a good predictor for whether it's a good variable name or not. And to get that kind of information, we really need to do some human subjects testing to basically see, what do analysts really think about how good these variable names actually are that are being predicted by the system.
Thank you, Ed. We have another audience question that is about Prolog. It's from Cory, not this Cory, Cory Redfern. So trying to understand one of the main points with monotonic tabling in Prolog is the recompute speedup based on rules being unchanged except for some numeric variables. So I think we'll go with Ed as well here because he's been working mostly with the internals of Prolog and the Prolog developers.
Yeah, so that's another great question, Cory. So the way that we computed the speed up is really simple. It's basically just a before and after. So when we say that there's 50 to 100 times speed up, that's literally we ran OOAnalyzer before and we ran it afterwards, and it it's 50 to 100 times faster now. The speed up is actually coming basically from redundant work. So the real problem with the way that tabling worked originally is that as we would get a new fact, we would basically have to recompute the entire table or the entire rule over from scratch. And as you basically get more and more rules as the system progresses, that continues to get slower and slower and slower. And so the real problem was for the largest programs where basically, we would compute a new fact, and then it would take on the order of hours before we could actually finish recomputing all those tables from scratch. So the speed up is really coming from that difference between computing everything from scratch and computing only the conclusions that could have possibly changed because of the new facts that we just got in the system.
And variable name work is very, people are intrigued. So there's another question related to that. Ed, this will be for you. The performance graph of the variable naming work makes me worry about overfitting. Any thoughts on that?
Yes. So, we did the normal approach of separating out our data into training, testing, and validation sets. So we have we have pretty good assurance that we're not overfitting here because we're measuring based on our validation sets, which have no intersection at all between the testing and training. In practice, we've been using this model more and more for experiments, and I could just tell you that anecdotally, as I talked about in the presentation, you don't always get the exact original name of the variable. And I would say, if you're looking at completely new code, it's not uncommon to get a different variable name. But what I've seen in practice is that you do get something that is very related to the behavior of the code that you're analyzing. So again, to me, as an analyst, that's really what I want. I don't really care if I get the original variable name exactly right or not. I just want something that tells me how that variable name is being used. And anecdotally, it seems like we were able to do that pretty well.
I'd like to change, if there's no other questions right this second, I'd like to change gears and talk a little bit about path analyzing. Cory, so that work was broad in that you evaluated many different foundational technologies, Pharos, Seahom, Spacer. It encompassed a lot of things. So what is the future of that work? How do you take all these results that you've generated over the last few years and chart a path forward?
Thanks, Jeff. Great question. We're continuing to look at all of those techniques. We're maintaining the infrastructure in the Pharos system, the Pharos function summaries, and the weakest precondition code ourselves in the GitHub repo. But we're also continuing to look quite a lot at that new Ghidra plus Seahom approach. As you know, because you were involved in the meeting last week, we had another conversation with Dr. Gerfinkel and his student just a couple of days ago since that recording was made. And we talked about the remaining problems with the lifter and the difficulties in Ghidra and the maintenance of that tooling, some software updates that had to be made in our future plans for it. So we're going to continue to watch that pretty closely. The team's been using Ghidra a lot more in general lately for binary program analysis. We've got a Ghidra plugin for OOAnalyzer that we've been working on. And you've also got your own tech where you've been using the systems and the approaches that we've been testing for composing constraint problems in Z3. And I understand that you've been using that to do API behavior analysis. Mm-hmm. So we'll be looking forward to that as well. Great.
And then Ed, there was a lot of interest in the variable renaming work. Maybe we can finish up by talking about the future of that work. It's very compelling and love to see it keep going forward.
Yeah, well, I think there's at least two directions where that work is proceeding to move forward. One direction is in the operational sense. So we're continuing to really work on a prototype of this and kind of get it to the point where we can just distribute it and get it into the hands of analysts. And the good news is that we're, as I mentioned, we're really close. We're getting there. If this is something that you're interested in, send me an email, and we might actually be at the point where we could start to have some beta users of this, or maybe alpha users more accurately. But I think this line of work in general, where we're using machine learning to study artifacts at both the source code and the binary level, and kind of learning the connection between how these works is a really interesting topic in general. So, in the talk that I just gave, we obviously used that to recover naming information, but you could imagine using that to recover all kinds of properties at the binary level as well. So some of the follow-up work that we're actually doing on this is to try to use that on this kind of same technique on another problem that's related to decompilation, and that is actually recovering type information from binaries. So decompilers like hexarrays, they often get really confused when you have complicated types like structs and classes and things like that. So one of the things we're looking at is trying to basically do the same thing of getting lots and lots of data, trying to train a neural network to be able to predict the types that are being used inside of these programs, and even going a little bit a step further and giving names to these types.
Well, great. So we're just about out of time. So thank you, Ed. Thank you, Cory, for the presentation and for the great Q&A. Thank you, everybody, for attending. I'd like to mention that we are going to go into a 15-minute lunch break right now before we return to the afternoon program. If you have more questions about Ed, Cory, or my work at the SEI, you can always reach out to us through email at info@sei.cmu.edu. Thank you again for your time.